Alright, let's take a look at a new topic, which is matrix chain multiplication DP problems. So we're going to start off with a medium problem, and then in the following days I'll try to ramp it up with some harder ones to help you solidify your understanding. So let's look at 1039 minimum score triangulation of polygon. So the question is going to give us a list of different values. So each value is just the I don't know, I guess some value of each vertice. So basically, if we're given 3 values, then we'll have a 3-sided shape. If we have 4 values, we're given a 4-sided shape. If we're given 6 values, we have a 6-sided shape. So our goal is to cut these polygons into only triangle shapes, and then we have to calculate the total score if we cut it in that certain way. So you can see for obviously for a 3-sided shape, there's only one way to make a triangle out of it. But for a 4-sided shape, we have 2 different options, right? We can either cut it on this slash or the other slash, and they will give us differing results, differing scores. So the score of this first one is 3 times 5 times 7 plus 5 times 4 times 7, which gives us 245. So the score of the other option is going to give us 3 times 7 times 4 plus 3 times 5 times 4, which is 144. So this is our best option. This second method of cutting it. It gives us 144. So let's kind of see the intuition behind why it's considered a matrix chain multiplication. What does this have anything to do with matrices? Matrix chain multiplication? Let's take a look. So, okay, when you do matrix multiplication, you have, matrix 1, matrix 2, matrix 3. No matter what order you multiply them in, your final result is going to be some, the same matrix. But the amount of effort you need to take to reach that final output is going to be different based on the order that you choose to multiply these in. So let's say you have, so this is a 2x4, this is a 4x3 dimension, this is a 3x5 dimension matrix. So if you multiply these two first, then let's see what the total number of operations you have to do is. So 2 times 4 times 4 times 3. So this is 2 by 4 by 3. So this gives us 24 operations. And then the new resulting matrix will be 2 by 3. So then 2 by 3 multiplied with 3 by 5 will give you 2 times 3 times 5 is 30. So this gives you 54 total operations. You have to do 54 operations if you multiplied M1 and M2 first. What if we multiplied M2 and M3 first? So these two first, right? So 4 times 3 times 3 times 5 gives you 4 times 3 times 5 gives you 60. And then if you did the resulting matrix, which is 4 by 5, times with 2 times 4 times 4 times 5, that gives you 2 times 4 times 5, which is 40. So this gives you 100 total operations. So you have to do 100 total operations if you did M2 with M3 first, right? So you can clearly see that M1 and M2 should be multiplied first, and then you should multiply this resulting matrix with M3 to give you only 54 operations, right? So that's the better option. So that's kind of how we can use some sort of dynamic programming to, so if you can imagine if you have M1, M2, M3, all the way to M10, you can, try all the different options. You can fix like an I here, you can fix a J here. So this is like a 2 by 4, this is like a 4 by 3, this is like a 3 by 5, this is like a 5 by 4, whatever, right? So you can, fix the I at this 2 here, you can fix the J at this 4 here, and then you can try all the different values. You can try K1 here first, or you can try K2 here first, or you can try K3 here first, and see which pairing will give you the best, will give you the most optimal solution. And basically, yeah, okay, so I guess that's enough about matrix chain multiplication. You don't really need to know too much outside of that. I'll cover the rest of this sub-problem DP intuition with this problem's example itself. So let's take a look at a 6-sided shape, a hexagon, and let's give it some values like 2, 1, 3, 4, 5, 1, or 2, whatever. And so we'll fix an I point and we'll fix a j point. And then, so our I will be this and our j will be this, right? So I, this is like the 0th index, this j is like the last index. So then we can try making a triangle at this point, at this point, at this point, or this point, right? These are the different k's that we can choose from, right? We can have all the k values, k1, k2, k3. We can make a k value out of any of these values in between I and j, in between points I and j. So let's see how that would look, right? So if we were to choose this, then we would do this calculation, and then we'd have the leftover subproblem, which is this half of it. Or we could choose this k here and then have these two subproblems remaining, right? So you can see how we can choose all these different k's and then we'll just compute the rest of the subproblems. Yeah. So let's just say, for example, we chose a k here. So what's the value of I times the value of k times the value of j? Well, that would be 2 times 3 times 2, which is 12. So then from 12, you'll do 12 plus the subproblem of this left side, which is I to k, and then you'll do plus the subproblem of k to j, so which is this here. So the subproblem of I to k is pretty easy, right? Because you only have 3 values, so that's 2 times 1 times 3. There's only one way to triangulate a triangle, so that's 2 times 1 times 3, so that's 6. So 12 plus 6. And then this subproblem from k to j is another, it's a square slash trapezoid, right? We have 4 values, so from k to j we have to try, this becomes our new k then in this subproblem, and then this becomes our new I in this subproblem, and then our k's are these two. So we can try, triangulating it at this k value or at this k value, right? So you have 3, 4, 5, 2. So you can either triangulate these 3 first or these 3, right? So then that'll look like, either 3 times 4 times 5, right? So you get the point, right? You'll just keep doing subproblems and going down the line like that. And so the main recurrence relation you have to see here is that you need to take the value at I times the value at k times the value at j, and then you have to plus the left subproblem, which is dp slash dfs of I till k, and then you have another subproblem which is the right side, which is k to j. Okay, so this is your recurrence relation. This is the recurrence relation for matrix chain multiplication as well. This is a very popular recurrence relation, and you should just know it for this type of problem. So let's take a look at the code now. So a very short code. So basically you have a DFS. First of all, you pass in the I value that you start at, which is 0, and the j value you start at, which is the last value in the array of values. So then at each ij, you can try all the values in between them to be the k value. So that's what's going on here in the for loop. And obviously you have to set some sort of max number to start off with, and then you'll keep updating it with progressively smaller answers to each of these possible points at if you place the k at index 2, then maybe it'll update the min. If you place k at index 3, then maybe it'll update the min, blah blah blah. And at the end of each recursive call, you'll just return that answer for the min, for the temp min. And this line here, line 18, 19, this is just in case we've reached some subproblem. I guess if we reached some subproblem that was less than size 3, so maybe this was our subproblem we were working with, then obviously you can't triangulate that, so you just return 0. So I think that is a decent overview of this problem. Stay tuned for my next few matrix chain multiplication videos, and hope you guys learned something, and thanks for watching.